So let's describe their structure in terms of their particle separation, their arrangement, and their motion. So particle separation, particle, the things it's made up of, right? Separation, how they are positioned next to each other. Are they close? Do they have separation, right? For solids, they are tightly packed, and this is kind of a simplification of separation, but yes, they're right next to each other. They're not moving around. They're not separate. Uh, you can see this in something like a crystal, right? Certain materials will form certain patterns, and when you get crystals growing in the earth, depending on what material it is, you can get different shapes or different patterns of tightly packed particles. Liquids, the particles are close together, right? They're still close, like in the solids, but because the force, the electromagnetic force, is a little bit less, there is some separation, and they can move around, but we still think of those particles as mostly touching each other. On a macro level, that's true, right? You get in the water, you get wet because these particles are touching each other. But they can separate, right? You disturb them, they move around, like you see this drop in this picture. Gases are widely spaced, right? They are bouncing off everywhere. They have very little electromagnetic force acting on the separate particles, so they fill up the space that they are in. So their arrangement with solids, as we saw with that crystal, right? They form an organized pattern. Different materials form different crystals, right? Like salt crystals are squarish, but you can get lots of different shapes. Liquids, the particles are random. They'll take the shape of their container, right? That this connects back to that property of theirs. They're randomly arranged, so they will take whatever shape container they're in. And the same thing with gases, they are randomly arranged. There is no structure or organized pattern to them. Um, Particle motion. Do solids move? Yes, they do. Um, I know that might seem strange. The chair you are sitting on, the floor you are standing on, it is moving right now. Um, Particles and solids are vibrating about their position in the structure. So let's imagine like a salt crystal, right? It's squarish, it looks something like this. The particles are attracted to other particles around it. Oh, whoops, sorry. Due to the electromagnetic force. And all of these particles are vibrating back and forth and in different orientations. So my question to you, two questions actually, and I'd like you to again pause the video, think about these, write them in your notebook, is why? Why do solids vibrate? And then number two, are objects ever perfectly still? What do you think? So take a moment and think about those. Write your answers in your notebook. So why do solids vibrate? Solids, everything, all particles have energy. Everything has energy, right? And any amount of energy will cause motion. Um, and so a solid that has energy will be vibrating even if you can't feel it. Our skin, our nervous systems are not sensitive enough to feel most of these vibrations, but everything is vibrating all the time, all the solids, all the particles, because they have heat energy, right? Your chair, even if it feels a little cool, is still much warmer than somewhere like outer space, right? That heat is energy, and that heat causes the particles within the solid to vibrate back and forth. So are objects ever perfectly still? The answer is no. Objects are never perfectly still because they always have some sort of heat energy. They're always moving in some way. I know that might seem strange, but it is true. We will talk about the theoretical perfect stillness at some point, but not today. In reality, everything is always moving, even if it doesn't look like it. So we talked about this before. Liquid particles slide past one another and move with random motion throughout the container, right? Other forces can act on the liquids to make them move in certain ways, like in this case, gravity is pulling down these particles, right, to make them fall. Um, gases move rapidly in all directions, colliding with each other and the sides of a container, right? Gravity is also acting on these, but they're so small that and so light that and thankfully they're light. We have a big giant atmosphere above the earth, right? Because these particles can move up that high because they're so tiny, even though gravity is affecting them. So let's talk about transitioning between the states of matter. We can see our three states here, right? Solid, liquid, gas. And if we think about something simple like water, right? We could probably name most of these transitions, right? When solid water goes and becomes a liquid, it melts, right? Ice melts and becomes a liquid. When that liquid is becoming a gas, we'll often say it's boiling, right? If you're boiling a pot of water, the liquid is becoming a gas, or we might say the water evaporates. You might see this if you leave some water in a cup in your room overnight, right? It will probably be at a slightly lower level in the morning because some of those particles are evaporating and becoming gas. So even if you don't heat up the water, it can still evaporate and change from a liquid to a gas. Now when we go the other way, going to from a gas to a liquid, we call this condensation. If you ever wake up early in the morning and you go outside and maybe you touch a tree or you walk on some grass barefoot, you might notice that there's water in it. That's because there is water molecules in the air that are gaseous, and overnight they condense and they become liquid and they cling on to the grass or the plants. They condensate, right? And then maybe if you want some ice for your drink or something, you take liquid water, you put it in a cold place, and it freezes and becomes a solid. And the thing I want you to look at and remember here is, this, right? We talked about energy a little bit before, but these transitions generally occur as you increase the heat energy, right? You heat up solid ice, it becomes a liquid. You heat up liquid water, it becomes a gas. And then as you go this other way, it's a decrease in heat energy. So as we think of phase transitions going from one to the other, we need energy to do something to make these happen, right? If you want to go this way, you need more energy in the form of heat. If you want to go this way, you need less energy. You need to take away energy to go from a gas to a liquid or a liquid to a solid. So let's describe these real quick. Melting is a change from a solid to a liquid. The specific temperature at which a solid melts is called its melting point. For example, the melting point of ice is 0 degrees Celsius. Each material has a different melting point. This is one of the physical properties of things, right? Like certain metals have really, really high melting points, and there's other things that have really, really low melting points. But like thinking about water, that's the easiest one. 0 degrees Celsius is the melting point. The temperature, the amount of energy at which the solid water will become liquid water. So here you go. Beautiful picture of melting right there, right? So this is happening at 0 degrees. Even if the room is at like 98 degrees, the water itself is at 0 degrees when this is happening. Freezing. change from a liquid to a solid. The specific temperature at which a liquid becomes a solid is called its freezing point, another physical property. Again, if we're thinking about water, it's 0 degrees. So when you freeze water, right, you can see these really cool water crystals that are forming. And this happens at 0 degrees, right? So even if this is happening like in a freezer or something that's below 0 degrees Celsius, the water itself, when it's transitioning, is at 0 degrees. Boiling, changing from a liquid to a gas. Again, this is called the boiling point, the temperature at which this happens. For water, it is 100 degrees Celsius. There you go. There's some boiling water. The water's changing into water vapor, right? Or sometimes we call it steam. Another physical property. Evaporation. This one's a little bit weird when we talk about the other one. So it is a change from a liquid to a gas, but it can occur at a range of temperatures, including below the boiling point. So this can happen even when we're below 100 degrees Celsius for water, right? It does happen quicker at higher temperatures. Why do you think that is? Think about our diagram. Energy, right? More energy, more heat energy lets the water molecules escape, become gas, or whatever kind of molecules they are, quicker, right? But it is a much slower process than boiling. So evaporation, and there's no like evaporation temperature. It can happen at many temperatures. It's a little bit different than boiling. And we're going to talk about why this happens a little bit more as we keep getting into things. But here's a fun example, right? You hang your clothes on a line and you put them out in the sun, and even though it is not 100 degrees Celsius, your wet clothes or linen is dry the next day. That's because the heat energy is helping to evaporate the water and change it into gas, right? Condensing, right? A change from a gas to a liquid. This also occurs at a range of temperatures. So there's a boiling point for water, but water coming out of its gaseous form and going into its liquid form happens at a range of temperatures. This is true for all gas to liquid transitions, right? Oops, sorry. So that is what I have for you today. You're now gonna do some work and you're gonna continue to think about these phases of matter and these transitions and energy and all of that, and hopefully discover some new things as well. And hopefully, I will be there very soon to continue talking to you about science and chemistry. All right, thank you.